Axial Seamount is a seamount and submarine volcano located on the Juan de Fuca Ridge, approximately 480 kilometers west of Cannon Beach, Oregon. Standing 1,100 meters high, Axial Seamount is the youngest volcano and current eruptive center of the Cobb-Eickelberg Seamount chain. Located at the center of both a geological hotspot and a mid-ocean ridge, the seamount is geologically complex, and its origins are still poorly understood. Axial Seamount is set on a long, low-lying plateau, with two large rift zones trending 50 kilometers to the northeast and southwest of its center. The volcano features an unusual rectangular caldera, and its flanks are pockmarked by fissures, vents, sheet flows, and pit craters up to 100 meters deep. Its geology is further complicated by its intersection with several smaller seamounts surrounding it. Axial Seamount was first detected in the 1970s by satellite altimetry, and mapped and explored by BICES IV, DSV Alvin, and others through the 1980s. A large package of sensors was dropped on the seamount through 1992, and the new Millennium Observatory was established on its flanks in 1996. Axial Seamount received significant scientific attention following the seismic detection of a submarine eruption at the volcano in January 1998, the first time a submarine eruption had been detected and followed in situ. Subsequent cruises and analysis showed that the volcano had generated lava flows up to 13 meters thick, and the total eruptive volume was found to be 18,000 to 76,000 cubic kilometers. Axial Seamount erupted again in April 2011, producing a mile-wide lava flow and fulfilling a 16-year cycle that had been predicted in 2006. Geology. Tectonic setting. Axial Seamount is the youngest volcano and current eruptive center of the Cobb-Eickelberg Seamount chain, a chain of seamounts that terminates south of Alaska. Axial lies where the chain intersects with the Juan de Fuca Ridge, approximately 480 kilometers west of Oregon. It is a product of the Cobb hotspot, but now sits on an ocean-spreading center between the Juan de Fuca Plate and the North American Plate, offset by the Blanco Fracture Zone to the south and a ridge-built triple junction to the north. This position is not yet entirely understood. It is believed that the chain, formed over millions of years by the now inactive Cobb hotspot, is older than the mid-ocean ridge it bisects. Between 200,000 and 700,000 years ago, the hotspot was encroached by the tectonic spreading center, displacing it by as much as 20 kilometers and building up the 500 kilometers long Juan de Fuca Ridge. At least 7 spreading centers have been recognized, and plate measurements near Axial show that the ridge is separating at a rate of 6 centimeters per year, producing a complex system of oceanic basins and ridges. However, some scientists have questioned this theory, pointing out that the high density of the chain's overlapping seamounts is incompatible with such an origin, as a hotspot would form a well-organized, widely spaced chain. Although the exact nature of Axial Seamount remains unknown, its complex origins makes it one of the most geologically interesting features in the North Pacific. Structure. Axial Seamount is the most active volcanic site in the North Pacific. Study of magnetic delineations along the seamount have modeled the ridge's history up to 30 million years ago, and shown that growth has progressed mostly in the north, with some southward progression dating back 3.5 million years. The base of Axial Seamount is a long, low-lying plateau, and the eastern part of the seamount is defined by a series of linear scarps. Axial Seamount has two major volcanic rifts extending approximately 50 kilometers north and south of its main summit, as well as several much smaller, ill-defined ones aligned in a roughly similar pattern. Basins around the volcano increase its irregularity, making it unusually complex. Axial Seamount's summit is marked by an unusual rectangular caldera, 3 km times 8 km in area, 3 degrees in slope, and breached on the southeast side. The area is offset by the 2 rift zones and defined on 3 sides by boundary faults up to 150 meters deep. The caldera is roughly 50 meters deeper at the north side than it is in the south. Flows within the caldera consist mostly of sheet flows pocketed by lava ponds and pit craters. Less common are pillow lavas. Their arrangement along the caldera walls suggests that they were an important component in the volcano's early growth. There are several dome-like structures within the caldera with heights of 100 to 300 meters. There are several small craters within the region, the largest of which, nicknamed the DD cone, is 2 km in diameter and 100 meters in relief. However, most of the features do not range over 30 to 40 meters deep and 1 km across. The northern rift zone of Axial Seamount is a 5 km long ridge running 10 to 20 degrees northeast of the main caldera. The rift is pocketed by multiple fissures, 100 to 200 meters in length, as far as 7 km from axial volcano center, and reaching up to 400 meters long and 20 meters deep. The area contains high amounts of volcanic glass. A major eruption is still visible in the form of an elongated glassy lava flow extending off the caldera wall, east of the main rift line. Dives in 1983 found extensive low-temperature venting at the northern half of the fissure. The shorter, newer southern rift zone consists of a topographically plunging rift, surrounding by subtle, discontinuous faults. Camera tows along the southern flank reveal that the area is built of delineated sheet flows, small lava ponds, and lava channels. The youngest of the flows on Axial Sea Mount are aligned along the 2 rift zones, followed by flows inside the summit caldera. The oldest appear to originate from directly around the caldera, where most of the basalt is completely covered in accumulated sediment. This suggests a bilateral growth pattern, a trend also found in Hawaiian volcanics and other well-known seamounts, for instance Jasper Seamount. Axial Seamount's growth has intersected the growth of many of the smaller seamounts around it. The largest of these is Brown Bear Seamount, to which it is connected by a narrow ridge running roughly perpendicular to its western caldera wall. However, little evidence of interactions between the 2 seamounts has been found. On the other hand, Axial Seamount's southern rift zone bisects Vance Seamount by as much as 30 kilometers, creating a zone of intense fissuring at the northern edge of the smaller volcano. Interactions with Cobb-Seamount to the north are more complex, forming an unusual bent-spreading center. Quote, in addition, there are 4 smaller structures directly east, north, and south of Axial. History. Early history. The first volcanoes along the Juan de Fuca Ridge, including Axial Seamount, were detected in the 1970s by satellite altimetry. Axial Seamount's proximity to the western coast and shallow depth make it one of the most easily accessible seamounts in the world, and its unique geological setting and active state also makes it one of the most interesting, rivaling Davidson Seamount to the south in scientific interest. The first bathymetry of the seamount was compiled by the NOAA survey in 1981, as part of seabeam trials in the North Pacific. The survey was specifically meant to find and link seafloor hydrothermal activity to geomorphic features. 4 areas of increased temperature concentration indicative of hydrothermal activity were found, and the then unnamed Axial Sea Mount was among them. Submersible dives with Pisces IV and DSV Alvin in 1983 and 1984 discovered the first active black smoke events in the North Pacific. Soon after, Axial Seamount was named for its central position on the intersection of the Cobb-Eickelberg Seamount chain and Juan de Fuca Ridge. The same year, the National Oceanic and Atmospheric Administration founded its events program, providing impetus for studying the volcano more closely. Between 1987 and 1992, a variety of pressure sensors, tilt sensors, temperature probes, and seismometers were dropped on the volcano in what came to be known as the Volcanic Systems Monitors. Further bathymetries by the NOAA's discoverer in 1991 and R.V. Sun in 1996 detailed the seamount further, making it one of the best-known features in the North Pacific. Also in 1996, the New Millennium Observatory was established on Axial Seamount to study volcanic perturbations and the effect they have on hydrothermal communities. 1998 eruption. The 1998 eruption of Axial Seamount was preceded by several large earthquake swarms, common indicators of volcanic activity. The swarms correlated to magma movements in the volcano bottom. Pressure recorders deployed on the volcano between 1987 and 1992 recorded 5 instances of deflation in the summit surface, ranging from 3 to 10 centimeters. In 1991, the National Oceanic and Atmospheric Administration was granted access to the United States Navy's SOSUS system, a chain of submerged hydrophones in the North Pacific originally used by the Navy to detect Russian submarines during the Cold War. Since 1993, the NOAA has maintained a real-time monitoring system that alerts the organization whenever an event occurs. The hydrophones are able to detect even very small earthquakes by listening for the acoustic waves generated by T-waves. These waves can propagate over large distances with minimal loss in power, making them an ideal way to record otherwise unnoticeable submarine earthquakes. Over the course of the eruption, only 3 earthquakes were strong enough to register on land-based systems. However, they cannot interpret earthquake depth or what caused them. Between 1991 and 1996, Axial Sea Mount experienced a single earthquake swarm of over 50 events. Between May and November 1997, this activity increased markedly, with SOSUS recording 5 such swarms, culminating with a massive 11-day, 8,247 quake event around the time of the eruption, in January 1998. The seismicity began at the summit, but within 6 hours had begun to migrate south as well. By the 29th of November 1997, the swarm had moved south by 50 kilometers. This coincided with lava release along the summit and southern flank. The seamount remained absolutely quiet thereafter, suggesting the completion of an eruptive cycle at the volcano. In all, 9,055 earthquakes were detected, and 1669 were strong enough to be located. Earthquake activity was concentrated around the summit and southern rift zones, with the majority of events centered inside the summit caldera. Temperature probes and pressure recorders in the caldera recorded an average 0.6 degrees Celsius increase and 3.3 meters height deflation, respectively, during the event. This close monitoring gives the 1998 eruption the distinction of being the only submarine eruption ever observed in situ. The first post-eruption expedition was organized and conducted by R.V. Wickoma on the 12th of February 1998, which conducted conductivity, temperature, depth, and optical casts to unusual results. In May, a dedicated dedicated bathymetric survey of the seamount showed topographical changes along the volcano's southern flank, which estimated the thickest flows to 13 meters. In July, DSV Alvin made several dives on the seamount's summit caldera, followed in August through September by an extensive observation and collection program using ROVROPOS, confirming the bathymetric estimates. A sheet flow more than 3 kilometers long and 500 to 800 meters wide was produced from Axial Seamount's upper southern flank, on the site of what was formerly an active geothermal field. The southern flows were in an area marked by a difference between older sediments and newer, glacier rock, and the maximum ridge generated by the eruption at the crest of the southern flow was 13 meters high. The total eruptive volume was roughly 0.018 to 0.076 cubic kilometers. The development, eruption, and close monitoring of Axial Sea Mount provided a fertile model on submarine volcanic eruptions to scientists. Several scientific papers on the topic were published soon after. 2011 eruption. Seismic activity at Axial Seamount virtually disappeared after the 1998 eruption, and monitoring of the volcano was done principally with bottom pressure recorders deployed on the volcano's flanks, supplemented since 2000 by annual measurements using pressure sensors mounted on remotely operated vehicles and applied to local benchmarks. The sensors have shown that Axial Seamount is slowly reflating. Just after the eruption, the seamount was swelling at 20 centimeters per month, a number that decreased to 15 centimeters by 2006. In 8 years, Axial Seamount recovered approximately 50% of its 3.2 meters of pre-eruption swelling, and in 2006, William Chadwick of the Oregon State University and his associates calculated an eruption recurrence interval of 16 years, predicting the next eruption would occur in approximately 2014. Axial Seamount behaves in a more predictable way than many other volcanoes, likely due to its robust magma supply coupled with its thin crust, and its location on a mid-ocean ridge spreading center. It is now the only volcano on the seafloor whose surface deformation has been continuously monitored throughout an entire eruption cycle. This prediction was fulfilled when, in July 2011, a dive using ROV Jason discovered new lava flows on the volcanoes that had not been present a year ago. The expeditionary crew recovered 2 bottom pressure recorders and 2 hydrophones off the volcano, which together showed that the eruption had occurred during April, starting on the 6th of April 2011. Although the instruments recorded hundreds of seismic events, only a handful had been noticed by SOSUS and land-based seismometers, as many components of the system had been offline at the time. The volcano subsided by more than 2 meters and produced a 2 kilometers wide lava flow during the event, which was as much as 3 times larger than the 1998 eruption. Ecology. In 1983, a Canadian-American collaborative expedition, named the Canadian-American Seamount Expedition, visited the northwestern edge of Axial Seamount's summit caldera to investigate a persistent temperature anomaly in the region. In a series of 8 dives conducted by Pisces IV, the scientists discovered a vibrant hydrothermal vent community on the leading edge of a 300 meters fissure within the caldera. Vent temperatures were measured around 35 degrees Celsius, approximately 30 degrees Celsius hotter than the surrounding environment. Camera tows and submersible dives through the 1980s and 1990s revealed Axial Seamount's active state, including the only known black smoker in the Northwest Pacific. 3 venting centers have been recognized. The original site, named Chasm, a southwestern caldera field discovered in the late 1980s, named Ashes, and a site located on its southeastern rift zone, named Castle. All are primarily sulfide emitting. The temperature and composition of axial seamounts' hydrothermal vents changes over time, but always maintains a roughly common identity, as do the vents' individual microbial communities. Vents generally have a lower pH than the surrounding fluid, and are acidic and alkaline as a result. The temperature of the magma feeding the system is uncertain, and may vary between 300 and 550 degrees Celsius. Curiously, vent fluid are heavily enriched in helium, containing 5 times the amount of the element as similar vents in the Galapagos, and 580 times that of regular seawater. Tube worms of the Pogonophora family thickened the largest vents on axial seamounts, forming colonies up to 6 square meters thick in places. Smaller, less nutritious vents feed bacterial mats, smaller tube worms, and limpets. The 3 most common microbial groups are bacterial epsilon proteobacteria, archaeon thermophilix of the Methanococcus family, and archaeons of the Euryarchaeota family. The most common flora at axial seamounts' hydrothermal vents is the worm Regia piscae, which is found at hydrothermal sites of all descriptions on the Juan de Fuca Ridge, and is the base of axial seamounts' hydrothermal ecosystem. Other species on the seamount include the tube worm P. palmiformis, the sea snail Leptardrillis fusensis, the bristle worm Amphis ami, the Galapagensis, and the sea spider Sericosaura verone.